Everybody. My name is Cristobal, and we will be discussing optimizing maize nitrogen recommendations with UAV-based remote sensing. I chose this particular study because I like the possibilities of UAV-based remote sensing. I believe that it is necessary for precision agriculture to be successful and have a reduced environmental impact. Most importantly, it can be utilized to minimize workers' exposure to pesticides and improve their safety and long-term health. The study focuses on in-season crop nitrogen status diagnosis, which is crucial for precision crop nitrogen management. It used UAVs for remote sensing and conducted the field experiments with varying nitrogen levels and different maize varieties over the span of 2 years. The Nitrogen Nutrition Index (NNI) and yield were able to be determined using the RGB and multispectral sensors. The study established NNI threshold values and yield to construct the RF model of the different varieties of the maize used during the trials. An index value of 1 means there is sufficient nitrogen present, a value above 1 means there is a surplus of nitrogen, and a value below 1 means there is a nitrogen deficiency. The R-squared of the study was above 0.64, which is moderately high, so it shows that the predictions from the model are mostly accurate. The study I chose focuses on in-season crop nitrogen status diagnosis, which is essential for precision agriculture and maintaining nitrogen levels. They focused on corn, which is one of the most widely consumed crops in the world. By adopting high nitrogen use varieties of corn, there will be a decreased impact of nitrogen inputs and a decreased overhead costs for the farmer. They use UAVs, which are unmanned aerial vehicles, for the data collection using RGB and multispectral sensors. Multispectral sensors collect data outside our visible range and can be used to measure features such as biomass and chlorophyll absorption. The RGB sensor uses the visible spectrum to take high-quality photos for researchers to visually inspect the maize. Above-ground biomass and plant nitrogen uptake were determined using both the RGB and multispectral sensors. An effective NNI index was made and yield was able to be determined using that data. They were also able to develop the model using the agronomic optimal nitrogen rates to measure NNI and predict yields. The study was also able to establish NNI values for their model that can tell farmers when fertilizers should be applied and how much nitrogen is present in their crops. The experiment was conducted at Shangzhou Experimental Station in Beijing, China, in a field. A split plot design was employed with nitrogen levels as the main plot and varieties as the subplot. The 6 nitrogen levels range from 0 to 300 kilograms per hectare, and the 6 different maize varieties were NE30, NE31, AQ202, KY188, ZD958, and XY335. The study also used several agricultural practices and techniques, and the data was collected over a period of 2 years. The soil was a sandy loam mix, which is a typical soil mix for corn because it has good drainage and aeration, and nutrient holding capacity. The ground truthing was done by taking plant samples at various stages of growth and physically measuring the available nitrogen, biomass, and other parameters. NNI threshold values were calculated based on the critical nitrogen concentration and relative yield. Nitrogen recommendation strategies were also able to be established using the agronomic optimum nitrogen rates. The UAV remote sensing data was collected using a DJI Inspire 2 platform with RGB and multispectral cameras. The DJI Inspire 2 is around $2,000, but the sensors are far more expensive, costing upwards of $20,000 for the multispectral camera. Data processing involved image acquisition, stitching them together, and extracting the multispectral and visual information. Ground truthing and remote sensing data were analyzed using statistical methods, and a random forest model (RF) was developed for predicting agronomic parameters such as biomass, nitrogen concentration, nitrogen uptake, the NNI, and yield. Multispectral and visual data and nitrogen rate features were combined as inputs for the RF model. The accuracy of the model was evaluated using the coefficients of determination, R-squared, root mean square error, and relative error. Aerial agreement was also measured to determine the spatial consistency of the UAVs. The kappa statistic was also high enough to measure that the model was a success. The results revealed there was a variation in maize nitrogen status and yield between the 6 different varieties. The nitrogen rate, which is the amount of fertilizer applied to the plots, and hybrid choice also influenced the biomass, nitrogen concentration, nitrogen uptake, and NNI. Biomass and nitrogen concentration had a positive relationship where more biomass was present when more nitrogen was also present. The study was also able to determine the NNI values for the varieties and found out that they ranged from 0.99 to 1.17 in 2018. However, in 2019, the NNI values were 0.6 and they only went up to 0.71. The difference in NNI values could be attributed to climate conditions, plant response to the nitrogen present, or other factors. Using these values, agronomic optimum nitrogen rates were also decided, which was different between the varieties. The random forest model was also able to determine the biomass, nitrogen concentration, nitrogen uptake, NNI, and yield accurately. It is a machine learning model that is fed by the multispectral data, RGB data, and ground truthing sample data from the field. The RF model was able to accurately predict yield to R-square value of 0.66, which is significant, to be a valid model. The RF model was used to determine the agronomic optimal nitrogen rate using the ground truthing data and was able to make nitrogen predictions using the NNI effectively. The remote sensing was also able to similarly estimate the nitrogen status of the plots to the actual nitrogen concentrations determined in the field. Overall, the results show that using UAVs to collect data and run the data through machine learning model to adjust nitrogen concentrations to make nitrogen recommendations is feasible and something that is crucial for precision ag and optimizing agriculture. Something that was discussed in the study was that the NNI changed based on what variety was being used and what year it was planted, which highlights the need for a specific nitrogen plan for each corn variety. The NNI values were also dependent on the stage of growth and will change as the plant grows. NNI threshold values were able to be determined for the 6 varieties used in the trial. The remote sensing data was collected with the UAVs and it was fed into the random forest model, which determined the nitrogen status of the active fields. The construction of the agronomic optimal nitrogen rate was made using the NNI values and yield that can further increase the efficiency of fertilizer applications and maximizing yield. They also discussed how important it is to determine nitrogen status in crop management, and using the UAVs and RF model, they were able to enhance their ability to predict nitrogen status, which further enhanced their yield. Furthermore, physical traits such as leaf or stalk size can be determined using the UAVs, which can save time and labor for breeding for these characteristics. The study found that nitrogen nutrition index and threshold value changed over the years and with the varieties used. There wasn't a universal NNI threshold that would be effective for all varieties of corn, let alone a few. The UAVs were used to collect multispectral and RGB data of the corn. The data was then fused together and fed through a machine learning model called random forest, which was able to accurately predict nitrogen status in the corn. This approach has potential in corn production and plant breeding because we can feed the corn nitrogen only when it is necessary, avoiding over-applying, which can cause further runoff and waste even more money for the farmer. The NNI values can then be further used to determine which varieties of corn were more efficient during the trials and breed for those traits.